How do engineers model complex fluid mechanics systems? In recent days, the engineering community has been buzzing about how engineers model complex fluid mechanics systems. This topic is gaining traction as industries seek innovative solutions for fluid-related challenges. If you are curious about how these systems are modeled, you are in the right place. Engineers primarily use computational and mathematical approaches to simulate fluid behavior. One of the most common methods is called computational fluid dynamics. This technique employs numerical methods and algorithms to solve the governing equations of fluid flow. The Navier-Stokes equations are key to this process. Computational fluid dynamics allows engineers to simulate properties like fluid velocity, pressure, and temperature in complex geometries. The process involves breaking down the domain into small elements and solving fluid flow equations iteratively. This method is essential for understanding how fluids behave in various conditions. Another method used is multi-field coupling. This approach is particularly useful for systems where fluids interact with particles or solids. Engineers integrate computational fluid dynamics with other numerical techniques like the finite element method and the discrete element method. This combination helps accurately simulate dynamic interactions between fluids and solids. To representing the behavior of different fluids, engineers also relying on constitutive models. For instance, non-Newtonian or viscoelastic fluids requiring specific models like the Maxwell model. This model helps describe the stress-strain relationships in materials that exhibit both solid and fluid characteristics. Turbulent flows present another challenge. These flows are chaotic and requiring specialized models for accurate simulation. Recent advancements include diffusion models that capture the statistical properties of turbulence. These models allow for scalable simulations that track fluid particles over time. For granular or multi-phase flows, engineers develop closure models. These models predict particle segregation velocities by balancing segregation forces and drag forces at the particle level. Validation against discrete element method simulations ensures these models are accurate. In practice, engineers select or combine these methods based on the system's complexity and fluid properties. The modeling process often starts with defining the geometry and boundary conditions of the system. Then, appropriate fluid models and constitutive relations are chosen. Next, the domain is discretized for numerical solutions. Engineers run simulations using iterative solvers and validate the results against experimental data. These techniques are vital for predicting fluid behaviors in various applications, including aerospace, automotive design, chemical processing, and environmental engineering. As industries continue to evolve, the methods engineers use to model complex fluid mechanics systems will likely adapt and improve, ensuring they meet the demands of modern engineering challenges.